We are in Rosen, Discrete Mathematics and its Applications, section 13.2. We're discussing finite state machines here with output. Here's the topics covered in the section. And what are finite state machines? Well, computers are finite state machines, and so we can model computers with finite state machines, but we can model many functions with these theoretical machines that we will construct in this chapter. And they are not exactly like flowcharts, but they kind of have a similar appearance, and they are used to trace the performance of the functions that a process will do or a computer will do. And so the way that they will work is that they have a finite set of states, usually mutually exclusive, designated starting state, some kind of input alphabet. Then we need a transition function that assigns uh, a next state to every state and input pair. And then some types of finite state machines will produce outputs. We would also need an output function. Others don't produce output, but they uh, perform their function by going to certain types of states called accepting states. How are they used? Many applications of them are used. Spell checking, speech recognition, uh, network protocols, uh, lots of ways that you could use a finite state machine to describe how an algorithm should perform its work. Well, we're going to start with a neat example, I think. It's an example of a vending machine that we're going to model as a finite state machine. And it takes three types of uh, coins as inputs: nickels, dimes, and quarters. Um, and then we'll have a rule that when 30 cents is deposited, nothing is retained after that. Any amount over 30 cents gets returned as change. Another type of input that a vending machine normally has is press a button. If you press an orange button, you get orange juice. If you press a red button, you get apple juice. All right, so what kind of states will this machine have? Well, it has the state uh, 0 through 6, where um, each state represents a multiple of 5 cents having been deposited into the machine. So 0 up through 30 cents. And we start in state 0, S0, with 0 cents received. Again, our inputs are nickels, dimes, and quarters, an orange button, and a red button push. Outputs are nothing. You can have nothing happen when you put an input in. You can get money back as change, 5, 10, 15, 20, 25 cents in change. And then, of course, hopefully, you'll get your orange juice or your apple juice as an output. So we have what we use is a state table to define the functions that are required for an output machine, a finite state machine with output. We have inputs, which are the states that the machine is in, the state that the machine is in. Another input is the coin inserted or the button pushed. So you have the same inputs for both the uh, state transition function and the output function. And we'll just start in state 0 and start depositing nickels. So we start in state 0, deposit a nickel, go to state 1, deposit another nickel, go to state 2, deposit another nickel, go to state 3, deposit another nickel, go to state 4, deposit another nickel, go to state 5, deposit another nickel, and go to state 6. And what happens? Well, let's look at the output function. We would just what we'd expect. Nothing happens because we haven't put in enough money yet for anything to happen. So it's just building up the deposit in the machine when we get to state 6. At state 6, if we put in another nickel, we don't retain anything over 30 cents, so that nickel comes right back to us as an output. And similarly, if we're in state 6 and we deposit a dime, we stay in state 6 and that dime gets returned to us. And if we're in state 6 and we deposit or state 6 and we deposit a quarter, then that quarter is going to come back to us. Um, Now, if we are in state 6 and we push this O button, if we pushed it anywhere up here, once again, just as we'd expect, nothing would happen. But once we're in state 6, right here, we push that O button and we go to state 0 and orange juice comes out. Or if we push the red button, we go to state 0 and the apple juice comes out. So we need two functions, a state change function and an output function. There are two valued inputs, which includes the state and the input alphabet. Let's take another look at this problem using what's known as a directed graph, where each state is a circle or a vertex of this directed graph, and then the edges represent transitions, the state transitions, and then the labeling on the edges contains both the input and the output information. So here's a digraph representation of our finite state vending machine. And we start in state 0, and I'll just trace that nickel input sequence we did. So here's 5 cents, nothing happens, we go to state 1. 5 cents, nothing happens, go to state 2, and so forth, all the way out to state 6. And here, if you put in 5 cents, you get 5 cents back, and you stay in state 6. And of course, if you push the R button at that point, you're going to get apple juice out, and you go back to state 0. Trace another path through this. We're going to put in a dime followed by a quarter, get 5 cents back, and we're going to get some orange juice out. So we start in state 0, we put in 10 cents, and we go to state 2, put in a quarter, oops, wrong one, put in a quarter and get 5 cents out, but we go to state 6, and then we push the orange button and we get orange juice out and go back to state 0. And there's the vending machine version of a finite state machine with output.